Guess we can start. Hello, everyone. Thanks for coming. Today I'll present a joint work with Shayon, Dave, Enrique, and Bart, ZeroTouch reinforcing RSS for secure geofencing. This work has been accepted at ACM SACMET, and I will present it in a few weeks' time. So let's begin. First, I'll briefly introduce the topic. We'll see what is the system and threat model. Then I'll give a brief overview of our system. I'll talk a bit about anomaly detection, and then we'll see our simulation results, and I'll conclude the work. So let's begin with the introduction. So first things first, what is geofencing? Well, it's a virtual demarcation of physical spaces, and these physical phases can be either inside or outside. So for example, here, we can say that the castle is one space, the garden in front is the other, or if it's inside, like the office B17 has some special privileges, or the master student area also has some traits. So the question is, why do we need this? There are many use case examples. First things first is the access control. So you can enable or restrict certain services based on the user location or based on their geofence area. You can also use it in logistics or smart home automation. So it's a wide range of applications, and it's used a lot in IoT devices, for managing the IoT devices. So what are the pillars or the enablers of geofencing? Well, first we need to rely on location in some way. And since we are in a wireless setting, we need to determine location physically. So where is exactly user, meaning the coordinates, the physical coordinates. And then we want to do this securely, meaning that we want to determine location in a secure manner. That is that the authenticity and integrity of the location data is ensured. So how do we do this? Well, effectively we need to do ranging. We need to determine a physical range. And since we are in the wireless setting, there are radio waves, and they have certain physical properties. And the core is that we need to measure certain things. So we need to measure things at the transmitter and at the receiver. For example, the received signal strength, time of flight, phase of arrival, etc. And based on this measurement, which is a function of range in some sense, we will determine a range under certain assumptions. Here I highlighted the assumptions mostly because in security, when we make assumptions, we make mistakes. So that's why this can be tricky to do securely. So how do we do secure geofencing? What are our main research questions? Well, first we want to focus on the indoor IoT environment, where usually the exact location is not really necessary. Also, we don't really want to rely on some extra hardware, so we want to keep it simple because mostly IoT devices are simple devices, and we want to have a rather small deployment overhead. So what do we propose? We propose a machine learning-based approach that leverages just the received signal strength. So something very simple that any IoT device can measure, and based on multiple receivers, we try to improve the security of geofencing. And we look at this as an additional layer of defense, similar to Swiss cheese model, if you've heard of it. So, what is our system and threat model? Well, we have to have some general assumptions. First things first, we assume that certain area, for example, a room, which is a geofence, contains and pre-installed wireless devices, and we call them anchor nodes. And we assume that they are also connected to the network, for example, maintain a secure connection with the server, and they are capable of performing the RSS measurements. So these are our three main assumptions. Note that we only need to know that there exists a certain number of devices inside the room. So the first question is this a valid assumption? Well, nowadays, there's a growing number of IoT devices, as you can see here. So it's reasonable to assume that nowadays, modern smart house will have a certain number of devices already in place, either in kitchen or bedroom, smart lamps, etc. So there are many IoT devices that can be already looked at as anchor nodes. So, what about the threat model? Against what are we trying to defend against? Well, we mostly focused on adversaries that are external, meaning that someone from the outside, the secure geofence, for example, a room, tries to trick our system to bypass ZeroTouch and to bypass its boundary detection. We also assume that the adversary does not have to play by the book, by the rules, so it can actually transmit the power at different rates. So the logical thing as an attacker would do is, if you're outside, you would transmit at higher powers. So we assume the adversary can do this. And the adversary has the knowledge of the anchor nodes which are positioned inside the secure geofence, that is a room. And yeah, we also assume that the anchor nodes are tamper-proof, meaning that they cannot be tampered with adversary prior to the boundary detection process. So any telecommunication engineer would say, would maybe have problems with this assumption, because we see here we say omnidirectional antennas. So the question is, what about directional antennas? What if the adversary has a complete knowledge of the anchor nodes and has perfect directional antennas, meaning that it can target each anchor node individually? We acknowledge that this is not something we are trying to defend against. Technically, if you rely only on receive signal strength, which is a rather simple measurement, if the adversary has this kind of power, there is no defense. But we argue that because it's a more realistic scenario, when someone just tries to increase the transmit power, which is a natural thing to do, that's our focus we are trying to address. So, how does ZeroTouch work? Once again, we need to determine whether the device is inside or outside, meaning inside the geofence or outside. And we want to use the RSS to do this. We don't want to have any interaction with the user and no additional hardware. And we want to do it as smoothly as possible. So, how do we do this? Our protocol is divided in two main phases, the initialization phase and the verification phase. And these reflect train once, verify many approach, that meaning the initialization phase should be only done once in a while, so not often, and you can easily verify if a new device is indeed inside or outside. So, the initialization phase. What is the core idea here? Well, here the idea is that the anchor nodes already present inside the room need to capture the RSS profile of a room, meaning that they will exchange some messages, and by exchanging the messages, they will record the corresponding received signal strength, and by that capture the profile of a room. For example, this guy here will start talking to this guy and record the corresponding RSS. Same for this guy, same for that guy. And when they capture all the RSS between each other, they will be forwarded to the central server, and central server will do some processing, meaning the training the neural network, which we will circle back later. And that's basically it from the initialization phase. Yes, if the environment changes considerably, meaning that the furniture setting changes or the number of occupants in the room change, then retraining is recommended, but it's not really necessary to retrain or do the initialization phase all the time. Now, when we have this, we have the verification phase, where we have a new device depicted in orange here that tries to prove that he's either inside or outside. So the idea here is that this device will again talk with the present anchor nodes in a room. The anchor nodes again will record the corresponding received signal strength and forward these measurements back to the central server. And central server will run these measurements, and based on the trained neural network, it will actually see if the measurements are coming from a device that is inside or outside. Note that here in our approach, the anchor nodes or the IoT devices only need to record the RSS, so they don't need to do any computation, so it's relatively lightweight on the anchor node side. So, the question is now, what is our neural network that we are using? Here, we look into autoencoders. Very briefly, autoencoder is a type of neural network for unsupervised learning, and mostly consists from two parts, the encoder and decoder. So the encoder tries to compress the input into lower dimensional representation, and the decoder takes that input and tries to reconstruct the original form. And basically the autoencoder or the neural network learns to do this as accurately as possible with the least amount of error between the reconstructed data and the original input data. So why is this interesting to us? Well, let's see how can we formulate the classification problem. So here, remember, the anchor knows forward the RSS measurements. So the input to our neural network is actually a set of RSS measurements. And we need a function that will, based on these measurements, output the anomaly score and tell whether these measurements are coming from the device that is inside or outside. It will compare the value to some sort of threshold that is predefined, and we'll say, okay, 1, it's anomaly, meaning it's coming from a device that is trying to trick our system that is indeed outside. Or 0, it indicates a normal behavior. So why is autoencoder good to implement the function f of x? Well, mostly because when the autoencoder is trained on a familiar data, it will learn to reconstruct this data with minimal error. So remember in the initialization phase, we trained this autoencoder with the measurements that come from the inside devices, so inside anchor nodes. So the autoencoder is trained on this. And then when the autoencoder gets foreign data, meaning the measurements from a device that is outside, it will reconstruct these measurements with higher error. And based on that, we can say, oh, there's a higher error, meaning that this is probably coming from a device that is outside. So that is the core idea of reconstructing, the autoencoder reconstruction. Now the question is, how do we determine the threshold? So we will get some sort of error with the reconstruction. So how do we know if this error is above or below, or how should we basically classify it based on the error? And here we want to determine a threshold a priori, meaning that we only need to use the training data. So the RSS measurements obtained from the inside anchor nodes. It's basically we need to do one class classification, and we don't have negative samples. And we tried many statistical approaches, and the IQR method, which is one of the statistical methods, gave us good results. So, knowing this, how did we approach our simulation? We wanted to verify a large number of devices, transmitters and receivers. And that's why we decided to go with simulations and use wireless insight, which is a really powerful tool used both in academia and industry to model indoor radio wave propagation. And based on the generated data from this program, we will then import it to MATLAB, and in MATLAB we'll do all the processing, the training, etc. So, Wireless Insight is developed by Remcom, and it uses ray tracing approach, and it accounts for all the known famous propagation effects as reflection, diffraction. So it really takes into account all the things that happen to radio waves as they propagate. And in order to make our simulations as close as possible, we decided to import a complete floor plan of from an architectural model, so from a practicing architect, to make it as realistic as possible. And here you can see the apartment layout, so from different waves, so you can see that it consists from different rooms, from different shapes, different sizes. So what will we do? Then we put some points, as you can see with the squares or the cubes, depending how you look at it. And each cube basically represents one transceiver. And what we did in simulation is basically these guys will all talking with each other and recording the corresponding RSS. And that allows us to have a very big set of measurements we can actually test. We decided to go with 3 rooms with 3 different distinct shapes and sizes as our secure geofence area to test our system. So before we can actually do something with the measurements, we need to do some pre-processing. And the key step here is that in wireless inside, the measurements are static, meaning they're only based on geometry of a room and the environment, meaning that if you would repeat the measurement again, you would get the exactly same results. So to make things even more realistic, we added some noise on it. We did some data normalization, which is pretty usual procedure when training a neural network. So after we did that, we can proceed to train the neural network, and we decided to use a relatively simple autoencoder with only 1 hidden layer. We tested some more complicated structures, but they did not really yield better results. So we decided to keep it simple. And then, based on the reconstruction error, I repeat, we will perform the classification. So, what are our results? So, we define our scenarios based on how the anchor nodes are selected. So remember, we had a bunch of nodes that we were testing, and then we need to somehow select a certain subset to test if our system is working. And here we have 2 approaches. The one is the random placement, meaning that we randomly select a certain number of anchor nodes inside the geofence and say, okay, these guys are now active, and these guys will record our received signal strength. And that represents the setup without any human involvement. That's the thing I talked about in the very beginning of the presentation, meaning that you would assume that certain number of devices are already present and relatively randomly distributed. We also tested something we refer to as smart placement, where we deliberately move the devices to see how can we position the devices that might give us better improvement. And we refer to this as a human-in-the-loop element. So it's not completely zero-touch in this scenario. The user would need to move some stuff around, but it's still interesting to see how moving certain devices can change the results. And in both scenarios, we tested against an attacker that increases transmission power by 7 dB. That's basically the most natural thing the attacker would do. If you're outside the room, you have a wall in between, you have bigger distance, maybe some furniture, and approximately 7 dB is the loss you would get by transmitting from the outside. But we also tested a more advanced attacker strategy, meaning that the adversary would power sweep, meaning test various powers, because the adversary does not have to stick with one transmit power, he can test any. So we tested wide range of powers to see how our system performs against the, call it, stronger adversary. So first things first, random node placement. So here in the blue, you can see the selected number of anchor nodes, and you can see which classifications were incorrect based on the red star. So this guy here, it was incorrectly classified to be outside, even though it's inside. And these guys here were incorrectly classified to be inside, even though they're outside. And we can see that, for example, with in this scenario, it's 20 anchor nodes. We get, for example, around 80% accuracy. But with the same number of anchor nodes, just a different selection, we can see that we have a relatively different results. So big difference between the number of anchor nodes, the set of anchor nodes we used for our experiments. So here we see results for each room, and we can observe a few natural things. Is as we increase the number of anchor nodes, logically the accuracy would increase. Also, the accuracy is not same across all the rooms. For example, the room 2 is the smallest one and the most simple one. There, you need the least number of anchor nodes to achieve good accuracy. And of course, the larger the room, the more complicated the room, the more anchor nodes we need to achieve good accuracy. So here we can actually see and observe the reconstruction error. So if you look at the blue line, horizontal line, that's the actual our threshold. And in the green area are actually the devices that are inside. And we can observe that two reconstruction errors are above the threshold. And if we go back, these are these two guys. So these two guys had their reconstruction error larger than our threshold. Thus, they were classified as being outside even though they're inside. So in the red area, we can see the outside devices, and we can see that most of them have reconstruction error above the threshold, which is good, meaning that we're correctly classifying them as outside. So by observing this, we had some key observations. So it depends on the number of anchor nodes we are using. It depends, the accuracy also depends on the room type. It also depends on the anchor node location. So not every anchor node carries the same amount of information for our classification problem. That's why we came to smart placement of nodes. So by running experiments, we noticed certain things. We noticed that if we would select anchor nodes only from the border of a room, meaning the anchor nodes that are placed only next to the wall, we can actually get even better accuracy. So this we refer to as a light human in the loop element. So if you were to move some of your IoT devices closer to the wall to get approximate situation like this, you could improve the accuracy even more. And also it's worth saying that some IoT devices, for example, smart plugs, are already kinda fixed to the wall, so they're already in a good position, quote unquote. So here we can see that again, with the 20 number of anchor nodes, we can get even better accuracy. Here I present the results again in a table, and then we can see that we get now 90s or high 80s only with like 10, 15 anchor nodes, which was not the case before. So what about the power sweep? This was for 7 dB. Well, we've only noticed around 5 to 10% decrease in false negatives. False positives are obviously the same because they're only based on the inside devices which are behaving properly. So the actual power sweep does not improve the attack that much for the attacker. So what can we say about this? Well, we argue that strengths of our approach is that it's rather scalable. Meaning that each device is independently checked using RSS, and it's pretty flexible, meaning that user is not really required to change much in order to implement this. The devices that are already there can be used as an additional layer of defense. And it's also pretty customizable, meaning that based on the threshold we are using, we can either put the threshold lower or higher, depending if you want to have fewer false positives or false negatives, meaning that we want to focus usability or security. And then again, the core idea is that they don't really require any additional hardware. So any wireless device should be able to record the RSS, the signal strength. And yeah, as I said a bit at the beginning, there's a wide range of use cases. For example, in the healthcare applications or smart home automation. And it really is a complementary security layer that can be implemented easily on top of the existing authentication protocols. So, what are the conclusions? There are a few key takeaways I would like you to take home. First is that secure localization is really essential nowadays in IoT devices and systems, and that RSS, which is assumed to be not really secure and something that was a bit forgotten, still is useful if we leverage multiple receivers. And we do that with the ZeroTouch, and we try to introduce a zero interaction layer of security. Also, not every anchor node, meaning that not every measurement carries the same amount of information, meaning that some locations are more favorable than others. We have identified them, and with a small anchor node movement and replacement, the user can improve the accuracy even more. And also, ZeroTouch represents a scalable solution, and it is suitable for real-world deployments. So, thank you.